Have you ever wondered how a tiny atom can produce massive amounts of energy? This question led Albert Einstein to formulate one of the most famous equations in modern physics, E equals mach squared. In simple terms, this equation translates to energy equals mass times the speed of light squared. This equation, as simple as it seems, revolutionized our understanding of energy. It suggested that mass and energy are interchangeable, that one can be converted into the other. It unlocked the secrets of the universe, explaining how the sun and stars shine, how nuclear power and atomic bombs work. It's the cornerstone of modern physics, a pillar that supports our understanding of the cosmos. It's a concept that's as fascinating as it is complex. So are you ready to dive into the world of physics? Today, we're going to dive into the world of physics to understand what this mysterious equation really means. Scene script. First, let's break down this equation and start with the E. What does it stand for? E in mc squared stands for energy. But what is energy? In the simplest terms, energy is the capacity to do work. It's a fundamental concept that's woven into the fabric of our everyday lives. Picture this, you're driving your car down the highway. The car is moving, it's in motion. This is an example of kinetic energy. Kinetic energy is the energy of motion. Anything that moves has kinetic energy, from the smallest particles of dust floating in the air to the largest celestial bodies hurtling through space. Now imagine you're about to launch a rubber band across the room. You've stretched it back, it's tense, ready to fly. This is potential energy. Potential energy is the energy that an object possesses due to its position or state. In this case, the stretched rubber band has potential energy because of its stretched state. Once you let go, this potential energy transforms into kinetic energy as the rubber band flies across the room. But energy isn't just kinetic and potential, it can exist in many other forms. There's thermal energy, the energy of heat, electrical energy, the energy of charged particles, chemical energy, the energy stored in molecular bonds, and many more. Energy is like a chameleon, constantly changing from one form into another, yet always conserving its total amount. This is known as the law of conservation of energy, which states that energy cannot be created or destroyed, only transformed. So when we see the E in E equals mc squared, it represents this energy. It symbolizes this fundamental and universal concept, this capacity to do work, this ability to change and transform, yet always remain conserved. Energy, in all its forms and manifestations, is at the heart of the universe, driving everything from the smallest atomic interactions to the largest cosmic phenomena. So, the E in our equation represents this energy, which can exist in many different forms. Next on our list is M. What might that stand for? As we delve deeper into the fascinating world of Einstein's energy equation, we come across this seemingly innocuous character. But don't be fooled, for M holds within it a world of meaning. It stands for mass, a fundamental concept in physics. You might be wondering, what exactly is mass? Well, let's demystify this. In the simplest of terms, mass is the amount of matter in an object. But don't let the simplicity of that definition deceive you. The concept of mass is integral to our understanding of the universe. Think of an apple. When you hold it in your hand, it has a certain weight, doesn't it? That weight is a result of the apple's mass interacting with the Earth's gravity. Now, if you were to take that same apple to the moon, it would weigh less due to the moon's lesser gravity, but its mass would remain the same. The mass of an object doesn't change, regardless of where it is. It's the amount of matter that object contains. Let's consider another example. Imagine a car. It's much bigger than an apple, isn't it? And it weighs a lot more. That's because it has more mass, it contains more matter, it's heavier. The more mass an object has, the more energy it can potentially have, according to Einstein's equation. So when we look at E equals mc squared, this M is a placeholder for the mass of the object we're considering. It could be anything, an apple, a car, even a grain of sand. The equation tells us that the energy, E, of that object is equal to its mass, M, multiplied by the square of the speed of light, c squared. In essence, what this means is that mass, this M, is a colossal reservoir of energy. And this brings us to the profound realization that matter and energy are interchangeable. They are two sides of the same coin. In the equation, M represents the mass of the object we're considering. So next time you pick up an apple, remember, you're holding a veritable powerhouse of potential energy. Finally, we come to c squared. This may look a bit intimidating, but don't worry, it's not as complex as it seems. In Einstein's famed equation, c stands for the speed of light. Now, light is incredibly fast. traveling at an astounding rate of about 186,000 miles per second. When we talk about c², we're talking about that immense speed squared. Imagine for a moment, if you can, the sheer magnitude of this number. It's like saying that for every single second, light could travel around the Earth over 7 times. Now, square that. The result is a figure so vast it's hard to truly comprehend. But why is this number in the equation? Simply put, it's because energy and mass are related by the square of the speed of light. This highlights the immense energy that can be extracted from a tiny amount of mass. So, c² in our equation is simply a very large number, representing the speed of light squared. Now that we understand each component of the equation E = mc², what does it all mean when put together? Unraveling this equation, we see the profound relationship between energy and mass. It tells us that energy and mass are interchangeable, two sides of the same coin, if you will. In essence, a small amount of mass can be converted into a large amount of energy, and vice versa. Think about nuclear reactions, where tiny particles like protons and neutrons come together to form a heavier nucleus. In this process, a small amount of mass is lost, but in return, we get a massive amount of energy. It's exactly what happens in our sun, where hydrogen atoms fuse to form helium, releasing a tremendous amount of energy that lights up our world. So this simple equation, EmC², encapsulates a profound concept: that energy and mass are interchangeable, and that even a tiny bit of mass can produce enormous amounts of energy.